All right, so this is an important topic, which is panel data econometrics. Everything we've been doing up to this far is known as multiple regression, and it is a cross-sectional data. It's a cross-sectional data. Let me dissect it for you, what I mean by cross-sectional data. Cross-sectional data, I'll just ask you some simple things on this. Cross-sectional data, you have multiple individuals, households, firms, cities, but then everything is at a point in time, let's say 1 year. So that empty cars data that I gave you, it was 1 year. I didn't have to indicate that it was a year this, the year 1984 or something. No, I didn't, because it was just cross-section. So when you take observations at a point in time, that is cross-section. You don't need to order rank them. You don't need to, nothing. Cross-sectional. Cross-sectional. Time series are observations on a particular variable or even many variables, but with multiple times. So time series, your focus is on the time. And the way you arrange the timing is important. Ordering matters. It has to be in chronological order. Chronological order. When you combine cross-sectional and time series, you get a panel or longitudinal data. So this is where you have multiple observations on multiple time periods. Multiple observations, multiple individuals, multiple time period. Multiple individuals, multiple time period. Multiple individuals, multiple time period. So you have, if it is human beings, you have different human beings. And then the variables you're looking at each human being's height, his weight, his BMI, is this level, is that level, is that level for each person. And then you collect that information every year. Every year you're collecting that information. Now you have a chunk of individual in one cross-section, but you have multiple cross-sections. So that gives you time. It's a very, very big, very important information of data that you work on when it comes to panel. So in a panel data, individuals are indexed with I, representing individual. Yes, come here.
Yes, Doc. So does that mean that the time series can also be called a multiple cross-sectional?
Exactly.
Okay.
Exactly. Now, the time period is indexed by T. The individuals are indexed by I. The individuals number 1 to capital N, where N is the total number of individuals. Please, when I say individuals, I don't mean human beings. Individuals can be companies. Individuals can be multiple industries. Individuals can be multiple cities. So you can look at situations. You can be analyzing cities, crime rate in every city. Individuals can even be countries. You can be looking at multiple countries. Individual can be specific stadia. So maybe you're looking at stadia. It can even be, like I said, companies, like banks or insurance. The time period is 1 to T. If you start from 2000 and you end at 2024, T is 2024. T is 24. Now, there are two kinds of panel. One is balanced, one is unbalanced. Who can tell me the difference between balanced panel and an unbalanced panel? Who can tell me the difference? Balanced panel and unbalanced panel. Balanced and unbalanced. Who can tell us the difference? Balanced and unbalanced. Oh, nobody? Yes, Emily.
Okay, Doc, so for a balanced panel, when you take the individual, either firms or whichever one you are looking at, all the years, so if you are using a 10-year period, they are going to have all the values for all 10 years. That's the balanced. But if it's unbalanced, then it could be that some of the years won't be up to the 10 years. So you can have some that are 6 years, while some will be the full 10 years.
Exactly. So the thing about balance, and I'm going to show you a picture that will make sense. So this is a balance panel. Check it. You see that you have 1980 all the way up to 1990. And on the far left, you see that they are all labeled as what? 1, 1, 1, 1. So this is all here. So how many observations are there? 11 there. From 1980 to 1990, that is 11. From 1981 to 1980, again to 1990 for the second group, for the second 11 observations. Then you have for the third 11 observations, all of them from 1980. So the information there is 11, 11, 11. Okay. And so therefore, we can say that the total number of observations is going to be 33. And for each of them, we have their GDP and then price, consumption. That is a balanced panel. Everything is in there. Now, when the data is not balanced, you can do something. So let's say that for the first observations, the first 11 observations, 3 of them were not there. We couldn't find their data. So that one, the numbers there are not 11, but they are, say, 8. So just because of them, the whole data set becomes unbalanced. What can you do to ensure balancedness in some cases? You can tell us. What can you do to ensure that the data is balanced in some cases? What can you do? If you want to ensure that the data is balanced, one thing you can do is what? Well, you can use something known as interpolation. You can use data interpolation to handle it. But please remember there are issues for interpolating the data, especially when you bring in some things that you are trying to ensure stability, when in fact there is no stability, it can affect it. If actually there is no stability, but the interpolation stabilizes it, because it's a linear interpolation. So that can affect it. Yes, Karen.
Doc, the unbalanced data, is it just about the year? Or if I have the year and let's say for maybe 1990, I do not have for GDP, and then for maybe 93, I do not have for GDP, does that also make it unbalanced?
That is what first of all made the year not having anything for you. That is what caused the year. So when you go to that year, you have nothing. That is it. It's not just that the year is not there. The year is always there. It's always been there. Now, is the variable you not seeing the variable in that year is what makes the year not there.
Right. Thank you.
That's what the year is always there. Something is always there every year. We are existing. Okay. Now, what are the advantages of going for panel data than using cross-sectional? And that's it. Some of the students I'm supervising, if Godol is here, and Emily too, I'm telling her, if you are dealing with your proper thesis, people doubt when you just go and pick a small data set to make a point. Increase your data. Larger sample is better than smaller sample. Larger is better. And panel will allow you to get larger. So why? Because it will increase the degrees of freedom. It will reduce multicollinearity. It will raise efficiency. Okay? That whole principle of best linear unbiased estimator, the blue, will exist. Okay? But the more you get more data to, it means you are bringing more problems. That's what it means. It means that maybe there are some information. Let's say that you take a data, and then the data is from 2000, but just because of COVID-19, you added 2000 up to 2024. Then you included COVID-19. Everything was looking good, but COVID-19 alone has disrupted the whole thing. It's caused a lot of issues. All of the issues will come in. It's like when you are growing, your responsibilities will increase. When you are 2 years, you have no problem. You can play and play and play and play. But it gets to a point. Sometimes some of you want to even go and exercise. You can't go and exercise. And your pot belly keeps increasing. The reason is because you don't have time. So you accumulate heterogeneity in the data. You accumulate it. But the question becomes the fact that you still get more information that has really happened. The thing actually did happen. Yes, there was COVID. You can't tell me that there wasn't COVID. There was COVID. Incorporate that COVID. So you get a better realistic assessment of what you want to assess. So more informative is the panel than the cross-sectional of time series. Theoretically, you can identify certain actions that have happened over time. In fact, when you have a panel, it can help you identify controls, dynamic relationship, policies that have happened. For example, there was a universal banking in Ghana. Which year was that? You are able to now incorporate the effect of the universal banking introduction, the deregulation exercise. And you are now able to now look at the impact of deregulation or impact of universal banking on the performance of the banking industry. You're able to assess, analyze using the panel data, but you can't do that when you get a cross-sectional data for 2023. Nothing has happened. So you can't actually say that I want to look at the impact of COVID. No, for you to get the impact of COVID, you must get data before COVID, data during COVID, data after COVID. So panel data allows you to do more analysis. Again, you can control the effect of unobserved heterogeneity, omitted variables, unmeasured variables, time, individual heterogeneity, all of them. Panel data will capture them for you. Will capture all of them. In fact, with panel data, you can do a lot of computational complexities, statistical inferences. You can do stationarity tests. You can do measurement error tests. You can do dynamic and dependent variable regressions. You can do GMM. You can do multiple kinds of panel analysis. You can do double machine learning and so many other things you can do. So panel is good. But panel is also not always great, like we have indicated. Okay. So this point was the point Kwame was asking. If your data has nothing available for consumption, that is what makes the year not useful. So at this stage, you have a choice. You may have a data for GDP, but you don't have a data for consumption. And you have a data for price, but you don't have data for consumption. So what do? This is where you may interpolate and then indicate the possible problems of it. Okay. Now, I want you to look at a cross-sectional model. This is a cross-sectional model. And this is a time series model. Who can tell me the clear difference mathematically between the two? The clear difference. Mathematically, when you look at it, what is the clear difference? Anyway.
Okay, Doc, so for the cross-sectional, we are looking at the individual firms or whichever one you are looking at. That is being represented by the I. Whilst for the time series, the T is being represented by time.
Exactly. So the key difference is that the same situation, but here you are picking the variables over time. But here you are picking the individuals across, individuals. You are picking the observations across individuals, and here you are picking the observations across time. That's it. That's the main thing. That's the mathematical derivations. Now, there could be endogeneity where the explanatory variable, the X, is correlated with the error term. Keep this in mind. This is a big deal, okay? When there are two kinds of endogeneity as people look at. The first one is when the explanatory variable is correlated with the error. Now, why is this a problem? Who can tell us? Why is this a problem? Because one of the assumptions of regression was that the expected value of the error term should be what? The expected value of the error term should be equal to what? Shama?
0.
So if it is 0, it means that in the error, you are assuming that there is no error. The error has been whittled down to 0. But then, if a particular independent variable is correlated with an error, then it means that error is not 0. That error is not zero, it's hidden. The error is unobserved. It's disturbance. It's hidden. It's stochastic. And it's hidden. And yet you are befriending a person who is hidden, has been quarantined. In a COVID period, the guy is hidden, has been quarantined, and you are correlated, you are associating, you are relating, you are linking with that person. So that's a problem. So you be infected. Once you are infected, you are an independent variable. But now you become kind of dependent because you are associating yourself with an unseen variable. You become infected. And this, you are an independent variable, and you are going to explain the behavior of a dependent variable. Someone is depending on you, a dependent variable is dependent on you. Now, because you've been infected, you're going to infect that person. So whatever explanatory power you claim you have may be coming from the infection that you have gotten. And the genetic is a big issue. It has to be solved. There are ways to solve it. So when you are doing a multiple regression, remember the simple regression. Okay? And now the simple regression will have I all through. All there. But then in the multiple regression, it changes. Okay? If you look at it, the multiple regression, all of these apply, but the multiple regression, we talk a lot about endogeneity. That's what I spoke about. There's weak exogeneity of the dependent variable. Okay? We wish there's weak exogeneity. And when there's endogeneity, like I've explained, it's a problem. We must have homoscedasticity. The variance of the error term must be constant. If there's no homoscedasticity, the beta coefficient will be inefficient, which means it's no longer blue, best. There must be no autocorrelation between the errors, the error of this, the error of that. And even in a panel regression, is worse. There mustn't be autocorrelation between error I and error J, and also across time. If you have any of these issues, last time we looked at it, you can use GLS, WLS, you can even use the newer West to handle it. But if you have a problem of endogeneity, you can use instrumental variable regression, such as the two-stage least squares, the GMM, and recently, other methods like Liebel, PSM that have been used to solve for all. Okay, so I want you to look at the general panel model. Look at it with your critical eye, maybe even write it. If I give you a general panel model like this in an exam, this is one where the beta has been transposed. Now, in this very example, this is a panel model, but the panel model has got one error term, which is the stochastic noise. But actual panel model has got three errors, composed errors. We'll talk about each one of them. You can use this one when you're analyzing some performance measures, when you have these errors. Let's try to look at each of the elements. Okay. Y is a dependent variable, which is a response variable, or the target. X are the regressors, the predictors, the independent variables. The alpha and the beta are the parameters. The alpha is constant. It has no economic interpretation. It's for beauty. So usually we can omit it. The key are the beta parameters, the estimated, which now become coefficient when they have been numerically estimated. Sometimes when you have gotten their actual numbers, you call them estimates. 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 So these things, you know them already. That's how I'm look at them. What you don't know yet are these. First of all, the XI. You see, the XI behave in a very strange way, and that's why I want to focus on. Look at it, the XIT, which is also the XIT. We know them as the explanatory variable. We know them as the regressors. We know them as the predictors. We know them as the independent variable. And there's something you got to know about them. Sometimes we call them environmental factors of interest. They have I and T attached to them, which means they change across individuals and over time. They change across individuals over time, which means that these X's, they are changing every year, every day, every month, depending on which variable you are dealing with. And also, more are added to it. Okay? So if they are particular GDP, new GDP is changing. So for the same country, that country's GDP is changing, and yet you have multiple countries. Each one has also gotten their own GDP, and those GDP are also changing and changing and changing. So it's changing across individuals, which is countries, and it's changing across time for each country. That is the most powerful one. And there can be many of these independent variables. That takes us to the errors. The errors are decomposed into UI. Remember, they are UIT. The I part is the individual specific effect. The lambda T is a time specific effect. Sometimes we call it time damage. And then the epsilon IT is the actual noise, is the actual stochastic noise. That one is changing across individuals and across time. That error is normally independently, identically normally distributed with a zero mean and a constant variance. You know this already. So that UIT is made up of several things. It's now a composed error. And it can assume strict exogeneity. In other words, we can assume that the expected value of this error, which is composed, there are three things in it. Given the independent variable, because we are ensuring that there's no endogeneity, the expected value is supposed to be zero for every time period that you look at. I can just ask you this an example to explain the elements. That's it, explain the element. Now let's go back to the x's. There are three kinds of the independent variables. One, we have varying regressors. A person's annual income, they have the IT. We have those regressors that are changing. For example, your salary every year is changing. It changes between person to person and also changes across time. This is a typical example of a varying regressor. And then you can also have time invariant regressor, which means if they are time invariant, it means they are individual constant. That's what it means. So look at that. That one is what? XI. So they are not individual constant, they are individual varying because they are time invariant. Time invariant means they are time constant. Invariant means it's not changing, so it's constant. The time invariant means time constant regressors, which means they are constant when it comes to time, but they are not constant when it comes to individuals. That is why they are only XI. So they are changing from individual to individual. Let's take, for example, race. If your race is white and I'm black, it's not changing over time, but across individuals it's changing. Between me and somebody in the UK, that person is white and black. That is changing across individuals, but it's not changing across time. So for each one of us, our race will be the same thing every year. So time is irrelevant. Time is irrelevant. Then you have another kind of regressor, is the opposite of this, which is rather changing over time, but it's stuck. It's constant across individuals. Oh yeah, there are things like that. Like time. Time is always changing over time. Time is changing over time. It's moving. Time is moving. The unemployment rate is changing over time. The interest rate is changing over time. The GDP changing over time. But then across individuals, it's the same. But between you and I, it's the same. The GDP is the same for you and I. But it's changing over time. So these are the three different regressors or predictors you should know about. Now we go to the first error. We said that one of the error is the one that is changing across individuals. We call it unobserved exogenous time constant, time invariant, individual specific factor. It's changing across individuals. Sometimes we call it the unobserved heterogeneity. It has no time index attached to it. Everything is individual index. It will tell you the characteristics of the person. It's hidden all. It's hidden inside the observation. It's hidden inside the individual. But your goal is to remove it. But it's not easy to remove. Let's say that you tell me that a person's salary is 20,000, but now you realize that a person has got special skills. Special skills. So others don't know the special skills. The manager knows the special skills. He increases the salary. So the skills are affecting the salary that people don't know because it's not on a paper. It's not certificate. It is a special skill the person has learned on his own. I mean, there are so many teachers, but there are teachers who are teachers. That's a special skill. Doesn't matter which subject you give to them, you tell them to teach, they teach everything. Students enjoy and understand it. So that person driving the scholarship of the school, it is a special skill. You can't really measure it. It's unobserved. It's unobserved. You capture that characteristics, which will never be picked by the independent factor if you collect them. Okay. Special skills, special behavior, special quality, the kind of religion the person has, even race and gender. That is a UI. It can be a dummy. It can be a dummy inside a person. And then it can move the dependent variable. Okay, so this is the UI. What about the lambda t? I've said it. The lambda t is a symmetric time trend. It's a set of time varying dummies. It's changing. It's changing over time. It controls for technological dynamics, regulations, macroeconomic events. It allows for a shift of the intercept. That's why changes in the dependent variable over time is caused by these guys. It is said to be contemporaneously exogenous to the conditional error. So you can have a dummy. So you can say that every year, what is happening? What is happening to your salary yearly? The salary is changing over the years. So you capture that. This is an example. Okay, an example of that. Let's look at the final one is the actual error. The one you can't control, you just don't know how to handle it. The idiosyncratic error. So when it comes to regression, panel or no panel, the assumptions about regression are all about parameters, the errors, exogeneity of the regressors. All of these have led to different panel data models. So this is a typical example of a panel model. I want you all to look at this model I've written here carefully and tell me the mistake with it. Just the mistake done with the specification. Thinking through that, just a second. Okay, who has found the mistakes? Actually, Daniel Asano, are you here? Daniel Asano.
Yes, Doc, I'm here.
Yes, Richard.
Doc, let me just get, so I think one that I can see is the beta 6 info. It only gives information over the time, but I mean it doesn't consider the individual
It's not info, it's inflation.
inflation. Sorry, okay, inflation.
Who else? What do you see? What problem do you see? No? You need it in your exams. Yes, fine.
I think the model started without the beta knot.
But in the panel, we indicated that you don't need it. It will be absorbed in the error. But that's one question I've even already asked. There's a problem somewhere. Some of the variables you don't know. Okay, let me tell you. So this is productivity. Productivity. And you have life insurance. This is life insurance. So you are checking for every life insurance company, every company. For every insurance company, you can have life or non-life. Okay. And this is representing that, life or non-life. This is representing the credit risk, leverage, the log of total asset, GDP, inflation, pure technical efficiency, scale efficiency, regulation, and then the rest. There's one problem with this model, one major problem. You should be able to identify it, giving you knowledge of panel data. And they're coming, just so you know, you don't need to specify the constant, because it will be absorbed here. So one major problem is that life and non-life is a dummy. Life and non-life is a dummy variable. And because it's a dummy variable, you can't say that it is changing across individuals and across time. It's like the type of a bank being foreign bank or domestic bank. You are either foreign or domestic. So which of these two should be removed? Is it I that should be removed or the T? Is it I that should be removed or the T that should be removed?
Doc, the T,
Why?
because it's a dummy as indicated. It doesn't change over time with respect to time. But the I is indicating the levels.
What level?
The level, either one or two, or either life or non-life.
Now you're talking. Exactly. These are the questions. These are the questions. These are the questions. All right. So you can see that there is a lambda t, which is a combined effect of the time constant variable. And you can see that I've indicated that including the intercept. So if the intercept is there, that's why we didn't write it, capture it. So please note, when you write a panel data model, you don't need to indicate the intercept. You don't need to. I didn't say you don't have to. All right. So that is a specific panel data model. Now, we are going to use the data sets and then run some panel data analysis. So there's a particular data set which is known as wage pan. There's a data set which is known as wage pan. And business for I'm sure you see my screen. The screen is frozen. Let me restore. Because I know you will soon indicating that you don't see it. So you check your page, and you'll notice that I'm giving you a certain data set known as wage pan. Wage pan. I'm going to also use my R. Let me just close. I'm going to open my R. I'll encourage you to do the same thing. You're going to use this data to understand every aspect of panel data very well. You're using this data to understand the aspect of panel data very well. I'm sharing the screen, but I wanted to open the data because I wanted to open the data. So we are going to look at panel data in a long form, one line for everybody. Every time observation, you're going to see the data yourself. We're going to use real data to show the different models under panel data. And the data we're going to use is known as a wage pan. We're going to give a title to the data. Let me just tell you a little bit about this data set. For those of you who have opened the data, just let me know. If you have not opened the data, don't worry, you don't have to let me know. But if you have opened the data, let me know. If you have opened the data, you raise your hand. I'll just check something. Don't let me know when you haven't opened it. So I have Joseph, Ayoko, Jerry, Lee, Miriam, Emmanuel Kwame, Setorusu, Emily Yasan, Albert, and Susan. Okay. Now, so this data set we have the data set and we are going to give a title to it. These data involve some individuals in 1998, and the data was sourced from the National Longitudinal Data for Youth. It was from 1980 all the way to 1987. And the title of this, we gave it a title because the paper was itself published by Villa and Viber. And it was made up of 545 full-time boys, youth males. So they are boys, no lady. I'm talking about 1999. The data was a balanced data. Remember, look at the years from 1980 to 1987. Anytime you're doing a research like that, talk about your sampling data. Discuss a bit of things about it. So how many observations are we going to have here? 545 individuals, 8 years. How many observations are we talking about? Let me see if I can show you the data. How many observations? So this is it. Yes, Albert. you have 4,360. Very good. Now I want you to look at the data of open. At the bottom here, you will see that there is a number down here. 4,360. That's the total number of observations in the data set. Okay. Just want you to fill your data. And you must always have your data. And you should be able to go and read the Bella and Dbeck book. So we have that kind of information. There's something you should know about this data. The youth have just completed their schooling. By 1980, where our data starts from here, make it slightly bigger. By 1980, okay, all of the students are given a code name, 13 and all of that. All of the students have completed school by 1980. And they are all been working from that 1980 to 1987, over that 8-year period. They are very, very young, though. Very young. Their ages are, in 1980 alone, these boys, their ages were between 17 to 23. They've just entered the labor market, fairly new. And so they have an average of just 3 years of experience in the beginning of the 1980, which is a sample year. So let's take, for example, the first person. See, this is the first person, and we have his information. So in 1980, the first person had an experience of one year experience. This person was not Hispanic. He was not Black. And there are different kinds of, in fact, there are different kinds of information about the data. So the person is white. The person is not any of those, it's white. If you want to know some bit of information about the data, look here. Let me just show you some. So every aspect in your slide has got information about the data. The experience is completed at age 6. Okay? So that was 6 years of schooling. And that is added. So when you go and look at the Excel, if you look at the experience, schooling. Yes, Joseph.
Doc, I'm wondering whether I'm the only one who is not seeing your screen. I've opened the Excel file, but I'm wondering, I can't see your screen.
Okay, you don't see anything at all now?
Anything, nothing. It's just a photo that is showing.
What is showing?
Your photo.
Okay, guys, do you see?
Yes, Doc,
Yes.
you can see.
You can see your screen.
Yes, Doc, we see your screen.
So, Master, maybe you should log out and log back. So, when you look at this data, we are talking about schooling. Okay, let me go to the right here. You see education, where's that? Education. So this person has got what? 4 years of schooling. As the person started from that 6 years, so you can see the 14 years of schooling. You see there. The next variable is union. Remember, we are looking at their wages, or their wage is the main target variable. Union is set by collective bargaining. So it is equal to 1 if a person belongs to a union. You know, these days, you want to be part of the union, like labor union. So union is actually a categorical variable, a dummy. Then there is married. If the person is married, you have yes. If the person is not married, you have no. Again, confirm it with the data. So here, see here, married is 0. If the value is 0, that means the person is not what? Married. If it is 1, it means the person is married. Then ethnicity, Black, Hispanic, other. Okay, so the one I said is white, okay, the ideal is other. disability, whether the person is disabled or not. If it is yes, the person is having disability. If it is no, the person has no disability. So you see all of this information about the data set. Now, I had two data sets. When you look at one of them, it's called wage pan. And then the other one is called wage pan dummy. So I've dummified the data. Dummified it. Instead of using 0, 1 from some of them, I've actually used no, yes, and things like that. Again, I've dummified the data. When you click here, you see that the total number is 4,360 indeed. Guys, pay attention. You might see this in an exam. Now, rural. Does the individual live in a rural area? Region. Is the person in the northeast, north central, south, or other? Wage. Wage is the hourly wage in dollars. And when you look at the data as well, apart from the fact that I have the wage, okay, if you check the original one, I'm just toggling between the two sheets. You see that apart from the fact that I have the wage, I also have the log of the wage. The log of the wage, as you can see. So I've taken the natural log of the wage. So this is a natural. If you want to know, this the first one is 1.19. 1.19. That's the first one. And that is the natural log of the wage. So if you want to be sure that that is the case, it's simple. Just take the value of the wage, and then you can now take the natural log of that. That's it. You can check the wage dummy. So that one will have both. So that is the wage, and then the natural log is there. You can just create a column and see. You see that when you take the natural log of this number, you get that. So that's the data set that you have. You have the sector, different sectors. They are all dummies. Occupation, different occupation, they are dummies. Education is there. Log of the wage is there. All of the dummies are there. Now watch the year dummies carefully. So if you look at this one, the year dummies have been given. From 1981 all the way to 87, those are the year dummies. Those are the year dummies. I have the similar thing here, 1981 to that. Those are the year dummies. So if this person is a particular year, you will know. And if you look at it, the years are just there. So you can see that this one is 1, this one is 2, it's going downward diagonal. Because the years increase deterministically by 1. So we want to understand some questions, and these are some research questions. Has a return to education changed over time? By the way, the word return to education is your wage. So it's actually asking, has the wage changed over time? So we want to see, we have the wage, we have the nominal wage, and we have the real wage. The real wage is just the natural log of the nominal wage. What is the effect of union on wages? You remember union? How is the fact that when you belong to a union, does that increase your wage or not? These are research questions. We're going to answer in the work. How does this vary by worker characteristics? What are the key forms of worker heterogeneity generating the endogeneity of the union wages? With what form of economic sorting behavior in terms of union and non-union employment are the data consistent? And so many questions can be asked and addressed using the data. Now, check carefully. You notice that some of the variables change over time. Let's take, for example, go to some of the variables change over time. Let's take, for example, experience. What's that? Experience. Experience. Does it change over time? Yes. Now here in this very one, you are showing the experience square. Okay. I want to come here. This is experience. You can see that the first person, look at his experience. Experience is increasing over time. 1, 2, 3, 4, 5, 6. By the 8th year, he's got 8 years of experience. That that person actually started with no experience. But the second person, which is person number 9, yeah, this person had already gotten 3 years of experience. So by the end of the year 1, year 0, 1980, getting 4 years. So experience is one of the variables. Okay. Now look at marital status. It's also changing over time because these are young children. So their marital status were changing. Some of them were getting married. Remember, they are 17 to 23 years. And the union. Union, some of them didn't want to belong to union. Some of them go into union, drop out of being in a union, come back to being in a union, and things like that. These variables are varying. They are varying over time. They are the I. We are going to formulate them. So we are talking about young people whose experiences are rising deterministically. Other variables are fixed. They are not changing. Race is fixed. Education is not changing. Why? Because over that 8 years, you want to concentrate on the job. So you are not being educated. So there's no mental brain damage. Some of you are doing PhD, permanent head damage, because you are working and schooling at the same time. That is a wahala. That is your wahala. Your wahala is not that the course is hard. No, that is not your wahala. Your wahala is you're combining everything at the same time because you are captain. So sometimes you say that the course is hard, but it's actually because you are doing so many things at the same time. Some factors are not changing. Race, education, experience, because now it's quite interesting to say that experience is not changing. Well, we've already said experience is changing. See, if you take, for example, education, they are not going to school. So experience is considered to be fixed, roughly constant over the 5 years period, because they are not going to leave quickly to go to school. They want money. That's why they came in the first place. But even though such a variable is not changing, we can interact that variable with a year dummy to see whether over the years, whether education is playing a role. We want to test if the return to education, which is a wage, was constant over the period or not. Now, if we had gender, gender would have been one of the fixed variables. Okay. But we don't. And so it will be absorbed into the U-term. I'm just discussing a bit of the variable. Now, you're going to see that in our modeling, some of the variables will be logged. Some of the variables will be logged. For example, the log of the wage is there. So wage has been logged. What does that mean? Well, wages are measured in nominal wages, but they can be increasing from 1981 because of inflation. So when they give you your salary, your inflation can dampen the salary. So you are collecting 2,000, but then the inflation is high, so that can look like your purchasing power is gone down. So you got to correct for that by deflating the 1987 wages using the GDP price deflator. But then the deflator factor or the deflation factor for 1987 wages is the same for all persons. So instead of using that deflation factor, we can rather use the log of the nominal wage, which is cool because it's the same for everybody. The difference will simply be absorbed in the UI or the intercept. So in short, what am I saying? I'm saying that when you take the log of a variable, you are converting the changes in the variable into percentages. So anytime you are interpreting the variable, it's not going to be a 1 unit increase in this. No, a 1% change in this will lead to a 47% increase in that. So you're not changing the variable. Yes, Kwame.
Well, can you kindly take the experience bit again? At what point will the experience not vary?
Experience. Okay.
Yes.
Experience means that these children are getting their experience every year. So experience is increasing every year for everybody. So by 1987, the ending year, it is as though all of them have got the same what?
The same experience.
The same experience. So it is as though experience has not what? Changed. It's fixed.
Oh, right. Got it.
That is the concept of that. But suppose some were increasing the experience, others were not increasing, then in that case, it differs across people, and that is why experience will have played a role. So it is in that context that we fix experience. Okay. So if we use the nominal wage instead of the real wage, instead of the log of the wage, because the log of the wage is a log of this. Yes, Joseph.
Oh, please, I wanted to find out if we say experience is not changing really because they are all working over the past 7 years. In real terms, experience is changing because depending on what they are doing or whatever they are involved in, experience may vary or experience varies.
I agree with that. But what you just said is what kind of experience? Because the way we are measuring experience is years, number of years of experience. But what kind of experience are you measuring? You are measuring skills here, isn't it?
Yes, please.
Which is knowledge, abstract element, difficult to measure.
Okay.
So I agree with you. So it's just numerical values we are using. But if you want to look at quality of the experience, then that one you have to use some indices. Okay. Now, regarding your determining whether some variables are fixed, they are changing, they're fixed, and not changing, it's all up to you. And you can do whatever you like normally in real life research. You just need a justification from other people. So sometimes, I'm not the only one who has done this. These people have also done the same thing. Then you can proceed with that. So normally it's important to get a real wage, but it's not difficult. It's not easy to get a real wage. That is why we take the natural log of the nominal wage so that we can use it to represent the real wage. So when you take the log, if you can remember when we were solving the heteroscedasticity, we were taking the log of some of the variables, and you saw that when we took the log, we were able to prevent some anomalies. So taking the log of some variables is always good. But please don't just go and be taking logs anyhow. It has to be backed by theory or by practice. So using nominal wage can produce, some misleading results. So the key point of using the log of the wage instead of the nominal wage is to impose that percentage effect of the independent on the dependent. Another thing, some variables are logged, but also some variables have been squared. Let's go to the data center. And you see that some variables have been squared. So let's go to the far right. You can see that we have taken the square of experience. My experience has been squared, as you can see here. Experience has been squared. Why will you square experience? Why will you square experience? There are certain things in life that go up. You see, the word squared means that you are indicating that the thing is inverted U like this, or the thing is U like that. Because the down part here means is linear. The up part here means it's also linear. So you combine linear and non-linear. So you now have a non-linear. It is the squaring of that independent variable that brings about this. But what is the theoretical justification for squaring? Well, certain things can be squared. If there is a strong belief that some particular variable, it raises the wage, and it gets to a point, it reduces your wage. Okay. So let's take experience. So there are certain things that reduce over time. Okay. Remember, this is a kind of a manual work. Manual work. So as a person is growing over time, take for example, footballers. Footballers are very, very good. Their salaries are very, very high because they are very good. As the years roll on, as the experience increases, get to a point, experience will have a diminishing marginal returns. So that player, you see that the player is no longer playing at Man City or Man United or Arsenal. He's now gone to play for Leicester. By the time he realizes he's no longer playing for Premier League, he's now playing for Championship. And by the time he realizes he's playing for League One, or he's a coach. And as a coach, he's probably not earning more than when he was a player at his peak. So there is that kind of diminishing marginal returns to experience. And that is why some variables are squared. This introducing nonlinearity. This introduces parabola or polynomials into the data. But it also ensures that there is parsimony. Yes, Joseph.
Doc, please, I wanted to find out. So in the case of the footballer that you used, I was thinking the variable is rather age, because the footballer, as you age to a certain point, your strength begins to diminish and not the experience, my understanding. So I was going to...
You are very right. I had the age in mind, but because I was talking about experience here, I forgot. You are very right. It's the age. Yeah, the age. If you want to test whether there is linearity or your variable exhibits linearity or non-linearity, you can check it. I have a video here that will show you exactly how to test for linearity. You click on this video, it will take you to the place where you can watch it. But here's the thing. You can't just be adding a bunch of extraneous squares into the data. Then you're squaring this, and you're squaring this, you're squaring by heart. No. You got to identify that it is truly exhibiting nonlinearity. You got to use theory. You got to think. Go into the literature. So sometimes you don't even need to specify that the variable is square. You may have to use a nonlinear model, a model that is exhibiting polynomials or natural logs. So instead of using linear OLS regression, use nonlinear models. And there are several of them. Several of the machine learning models are nonlinear. Use that. Then finally, there are some variables that are called interaction terms. Interaction. So there are two predictors here, independent variables. All of them are affecting a dependent variable, but they are affecting them in such a way that it's no longer additive. It's now multiplicative. So let's take, for example, so you have X, so you have Y. You have Y being affected by B1 X1 plus B2 or beta 2 X2 plus beta 3 X1 times X2. So what you are doing here is that you are multiplying the X1 and the X2 together to see their combined effect on the Y. This is called interaction term. Sometimes, if they are all numerical, you want them to be on their own. But sometimes, especially if one is a dummy, you do that multiplication, it's also good. And what happens? You will know that, oh, this variable is affecting this, but in the presence of that variable, it's affecting it a lot. So actually, the two of them are working hand in hand. Yes, earth can do some great things. Fire can do some great things. Wind can do some great things. Heart. But when the powers are combined together, I am Captain Planet. And so you are able to see the real powerful effects with the combined forces. This is possible, but you need to justify it. In fact, these are ways to get research questions, actually. This is a way to be able to introduce a new thing into the literature. So sometimes everybody is looking at the effect of this effect, of that effect. Then you will bring this one as a moderating or interaction factor. Then you can see how the presence of this can affect the result. And like I said, interaction can be done when both independent variables are binary. You can do it. When both of them are binary, so you can multiply, a binary variable with a binary variable. So maybe one was 0, the other was 1. So the two will be 0. One is 1, the other is 1. The two will be 1. Okay, like that. And then you see the effect. You can also do it for one being binary and the other being continuous, like this one. Or all of them being continuous. You can also do that. Okay. So this is the wage band data we've been using to explain the analysis. If we use something called fixed effect, and we shall look at that later. If we use fixed effect, because fixed effect will eliminate all those time constant variables. All variables that are fixed are removed from the model. You see that. If we use that fixed effect, anything that is fixed, like ethnicity, like education, and I'm sure you know why, like experience, okay, they are going to be removed. There are many, and your question was, hey, why will you consider these factors or other aspects, education, okay, or experience? We said that roughly within the first 5 years, they will not go back to school. And so we can exclude it as part, but we can interact education with the year dummy. We said that too. So if it was a fixed effect model, that is what happened. So we are now going to look at the general panel data model, and then we can particularize it with our data. Okay. And that will be it. Okay. Then next time we shall go through the final nitty-gritties. So this is a panel model. This is a general panel model. Look at it carefully and smile. And smile. We know that the pooled OLS ignores potential unobserved heterogeneity. Pooled OLS. Okay. What it does is that across the groups of time, it doesn't even consider the time. So suppose you have the data. Emily, explain pooled OLS to them, because this one is so easy that I think you should be able to explain it. Explain what a pooled OLS is.
Okay, so Doc, from my understanding, when we are talking about pooled, it means we are going to deal with all the time periods. So in this case, it means you are going to consider OLS for all time periods as one.
Very good. What else? So if you have 6 companies in the first year, 6 companies in the second year, 6 companies in the third year, there are only 6 companies, which means you have 18 observations. Okay, that's what you have, 18 observations. You can choose to say that I'm not going to call them observations, I'm going to call them 18 companies. Okay, so what you're doing is that you're considering, each particular company or observation as a company on its own. This is done to increase the sample size, but it's also done to speak about them one time without incorporating time. But here's the thing, guys. If time is a big issue, you can't do that. If time is a big issue in your model, you can't just be going about and be doing this. You'll be punishing your work. So if you have this general model and we are dealing with pool, remember that the OLS estimator must be constant. The error term is not correlated with this. If it was, we'll have an indigeneity problem, this. So the OLS, if you go ahead and use OLS, you're going to have a trouble. That's why we don't use that. So we are going to go back to our model, and then in our wage band, we're going to estimate the wage equation for the young men. We are going to apply OLS as if there's no time. And therefore, we're going to include education and raise all of them. Okay? But when we get to the fixed effect, we'll drop them from the model, because fixed effect will assume that they are all fixed, especially the dummies. The time varying variables are experience and experience square. Union is also changing. A person is changing union, so we include union as a time varying variable, even though it is 0 and 1. And again, married, even though married is 0 and 1, we're going to include married as a time varying variable. It's changing over time. Why? Because these are children between 17 and 23, and that period, they are going to be married. So we allow, marriage not to be dummified. So we are going to write our model, specify a model for the purpose of the fact that we are going to do OLS. But this OLS, because we are lumping all the time together, we will call it pooled OLS. So this is our model for the general situation, And the specific one you see here is our pooled OL. Guys, I want you to look at this and tell me, what thing have you observed from this model? Specification of models is very important. What have you observed? What do you observe here? First thing you should observe is that there is no something. You can tell me. There is no
beta knot.
Sorry?
No beta knot, and that's in the error cell.
Very good. No beta knot. What else? No beta knot. That's true. What do you see about experience and experience square? Okay. You can see that experience has gotten a square there. Yeah, Richard.
Yes, but Doc, I can see that we are considering both the experience and the square of the experience for the individual.
About there is something that you should note about the labeling, the writing. Richard.
The writing.
Richard.
Yes, Doc. Yeah, so I think the difference between the experience and then the experience square of it in the same, equation.
Yeah, do you realize that everything is I?
Yes, everything is I.
Why? Why?
Because you said when you take the log, the time, the time is not needed, or time is not
No.
relevant.
I'm talking about the I. Why is everything I?
Doc, because you said the model is OLS. The model is OLS.
Yes. So it is OLS, then what?
Then time is irrelevant, or time will affect the results.
Time will affect the source. So what have we done to the time? Yeah. This is put OLS.
Well, I think we are using the fixed 5-year period.
Emily.
No, I think time is being treated as a dummy here.
Good. So, but do you see the way it's been written? Don't you sense there is a problem somewhere? If time is being treated as a dummy, how should it have been? How should it have been? Joseph? Your hand is up.
Doc, it's the old hand. I'm coming. I'm organizing my thoughts.
So, Emily, do you realize the value of the time, that the delta 181, should it be T? If it's being treated as a dummy. Do you get a point?
No, Doc.
If you say the thing is being treated as a dummy, if something is being treated as a dummy, do you add T to it?
No, it's supposed to be I.
To be I.
It's deliberately designed for you to think. What is the problem with this model? What is the problem with this model? if it is a crude oil. So please work out some of these things, but for me, that is a critical thing. Understanding is key. All right. So this is a crude oil for our specific data. Now, if crude oil is all you got to do, if crude oil is your only thing, in panel models with usual crude oils, there's a problem. You see, if you're going to use a crude oils, you're going to have a problem. But the thing is that if it is your own, that's the only thing you got to do. Then you have to solve the standard errors. Because the moment you use OLS or crude oils is the same thing, by the way. If you use the crude oils, the standard errors are going to be wrong. They're going to be biased. Unless there is no cluster effect. But there is always cluster effect. There are always groups. So in order to solve that standard error problem, you correct for the standard errors by using something known as robust standard errors in R. What a robust standard errors will do is that it will correct for not only heteroscedasticity, it will allow the cluster correlation and the heteroscedasticity to correct for the cluster sampling. So the standard errors now is like you are cooking new standard error. And as you know, you don't know, as you know, anytime we have the coefficient, okay, or the estimate divided by the standard error, that will be equal to the t statistic or the t value. Then you go and read the t value from the table and you get the p value. So if the standard error is wrong, you got to replace that. So the standard error is no longer going to be the standard error OLS. No, it's rather going to be standard error robust standard error. That means that it is correcting for heteroscedasticity and it's also correcting for serial correlation. So the OLS, the pooled OLS you are running is not just normal pooled OLS, but it becomes a pooled OLS with robust standard errors. That's sweet. The standard errors are robust. In other words, you are correcting the standard errors. So you are going to run that in R. And then you check your results to see whether you did a good job. So if you have your data, let me see what I can do. Each one. So there are so many things in here. But you guys can run your command using the code there. You got to load your data. Let me see if I can. There are so many things you can do and analyze this data. I just want to jump all the gimmicks. You have to do correlation analysis with so many things, graphical analysis, and so many things before you come to the real world. Right. Anyway, we can just do that here. Okay. Just go here, click scripts, just run your commands. So here, you can just copy this command to load your data. And to load your data, go to this one here. And you can just, I'm just using the wage dummy. Yes, I'm just using the wage dummy. So let me just run the wage dummy. I've just run it. Let me show the head of the data. So just do head, run into bracket, wage pan. That will show the head of the data. As you can see, this is the head of the data showing down here. Okay. Hope you guys are seeing my screen. Then,
yes, Doc, we can see.
Now you're going to run the panel regression model for the pooled OLS. So you can install this library PLM. You can install and load it. You can install and load it. So you first install, and then you load. You load that library PLM into the model. Now, if I run it, doesn't show in my case, I need to load. So mine is showing here that it's been loaded nicely, which means I've installed it. If you haven't installed it, just click on install here and type PLM. It will pop. PLM. And then you can now install it before you come and do what I've done. But I have installed it already. Okay, so once you have installed it, what do you do? You now click on, let's go to the next one. Summary. You can do summary package to get the mean of some of the variables, the descriptive statistics. So I can do some summary information. There you go. So I get some few information regarding the summary of each variable. It's not too important, but in every research you need to go. This one doesn't give you enough. So you can invoke the library pastex. Okay. I have installed it already, so I'll just load it. The library pastex. The pastex would allow you to do more descriptive statistics. In fact, it gives you beautiful and more descriptive statistics. Emily, you remember that we also use the describe after.
Yeah, psych.
After the psych package. In fact, all of you know. So you can use that. So I'm just running the descriptive statistics. Just watch. You can see that for each variable, let's take a particular variable like age, the age. You see that the age, you know what it gives me? It gives me the variables, the minimum value, the maximum value, the range, the sum, the median, the mean, the standard error of the mean, the confidence interval, the variance, the standard deviation, the coefficient of variation. It gives you so many things, and you can select whichever one you have. You can also use the library site, like I said. But that one is here. So when you use this one, library site, you can also get more descriptive statistics. So let's load that first. And then you can use this command, describe wage pan. It's going to give you more than the other ones, some of which the other ones before didn't give you. Okay. So this is it. When you run this, there you go. There you go. You get more things. So you see that one, it gives you the things in a beautiful order. So when you take, for example, age, you get the mean, the standard deviation, the median, the trend mean, the minimum absolute deviation. You get the ketosis, you get the minimum value range, skewness, all of that. Then these are all preliminary. We call it data pre-process. You can even describe by group. So let's say that you want to look at the group of male and female, the group of according to the year. Several things you want to do, you can do that. I don't want to go too much there. And then you can also generate correlation matrix. So this command, to generate correlation matrix, you need to install and invoke the H miscellaneous. Once you've done that, you can use this command to remove all the dummy variables. Because if you don't remove the dummy variables, you'll not be able to get your correlation coefficient. So you use this to get the dummy variables. You run this, and there you go. You get the entire correlation matrix. It's beautiful. It's beautiful. If you don't know that it's beautiful, I'm telling you it's beautiful. So here, this entire correlation according to 2 decimals. So all this, you can see that the right diagonals are all 1, 1, 1, 1, 1, 1. They're all passing through. 1, 1, 1, 1, 1, 1. So that's it. So everything else, you've been able to generate correlation matrix there. I'm not going to, of course, interpret any of these because we've done this multiple times, so you know. So let's go to the substantive matter. So now, I was saving this, which requires that I need to save. So let me just call it which part. So I can now do this. This is the main thing. PDIM. It will tell you the dimensions of the data, the panel. We are now going to do our panel analysis. Do PDIM to tell you the dimensions of the data. Run this, and it tells you, look down here. It tells you that we are dealing with an unbalanced panel. A T-1. Why is this unbalanced? I don't even know why it says it's unbalanced. Because it's supposed to be balanced, I think. Okay. So if you want to know missing values, you can also check for missing values. You can do a co-plot. It will show you the IDs position from the left to right, you know, of each of the years across the IDs. It's a beautiful work, but sometimes depending on the speed of your computer, you may not be able to get it immediately. So the co-plot of the wage. There you go. So on mine, you can see it there. You're able to see from 1980 to 1987, how are the individual years going? How are they looking like? How is the plot? What is the structure of this? You can do a scatter plot. Okay? Sometimes it might not show because it's too many. But let me try it and see. You can do a scatter plot of your entire data. There you go. Sometimes it might not work, like I said. So it might not work. Sometimes you may have to increase the, let me go here, increase the margins, stretch the margins a bit. And let me rerun it and see. Okay. Yeah. Okay. It looks like sometimes you need to. Yeah, when the figure is so much, might not work. Scatter plot. Sometimes you may have to use some. Anyway, these are all preliminary works that you can do. I don't want us to distract ourselves much with those that do not show. Some of them will not work. I need to just double check. And then you can plot the wage and the mean over time. The wage and the mean over time. The wage across the years over time. So I'm just using this one. So most of these ones you need to run, but you can see that mine was showing in the original work. So you can look at them. These are all preliminaries across years. This is how it looks like. You can see that they are all balanced here. Unlike the previous one. Maybe I need to use the previous data. Now, when you have done all of this, you are now ready to run your pooled OLS. Okay. So let's do our pooled OLS. And that's it for today. So we're going to do our pooled OLS by running this. Watch it carefully. Everything, the dummies have been added. You need to ensure an index. The index is ID. Then you include the year. And which model are we doing? We are doing pooled OLS. So you write model equal to pooling. And then you say that I want you to summarize the results. This will give you some beautiful results. So I'm going to just run this as the final thing for today. So this is it. This is the pooled OLS. Ladies and gentlemen, the results. It's loading, as you can see on the right. It's loading. And that's it. This is your results. Okay, it's been able to, you see this one, it tells you clearly that the balance is a balanced sample. So that's why I was quite surprised that the previous one was saying unbalanced. This one clearly says it's balanced. time periods are 8, the observations are 4360. And now you can learn to interpret each one of it. Remember, when you look here, it's a log of the wage you are using. So the interpretation will differ. We shall look at this next time. Ladies and gentlemen, that brings us to the end of the entire Kabbalah. What we've just done is that we've demonstrated the use of the full OLS. It gives you the total sum of squares. It tells you the value of the R square. We'll interpret all of these. And then on Wednesday, we'll wrap it all up. Wednesday, we'll wrap it all up. Yes,
just for clarity, so with the longitudinal data, the elements do not change. So if I'm collecting such data over time, and then someone decides that they don't want to be a part of the research again, or someone even dies, and so they are not available for the research, do I leave the data unbalanced, or I'm allowed to replace such persons?
Leave it unbalanced.
Okay.
Yeah. Any other question, please? Guys, I wish you all the very best, and I'll see you all on Monday. Next week, we'll be wrapping up.
This is a marathon.